Welcome to Scienceverse Expert Panel, the podcast where we dive deep into the minds of leading scientists and unravel the mysteries of our universe. I'm Anirban, your host, and this is our seventh installment to the Scienceverse Expert Panel series. Today, we have the privilege of hosting a brilliant mind in the field of theoretical nuclear astrophysics, someone whose work explores the extreme conditions of the universe, Dr. Rajesh Kumar. Dr. Kumar is currently a postdoctoral researcher at Kent State University and has dedicated his career to understanding the physics of compact stars and hadrons in hot and dense matter. So, without further ado, let's welcome Dr. Rajesh Kumar to the Science Lovers Expert Panel. Dr. Kumar, thank you. Thank you for joining us today.
Yeah, thank you very much, Anirban. Thank you for giving me this opportunity to share my views, what I do in my research. And thank you, ScienceWorth. It is really an amazing startup. I really like it. And I have also done some YouTube content as well. So I really like promoting science over the internet. Thank you very much for this.
Sir, could you just introduce yourself and tell us what you do?
Yeah, so hello, everyone. As Anirban said, my name is Rajesh, and I'm currently working as a postdoctoral research associate in Kent State University, Ohio. My main focus is to understand the extreme matter. When I say extreme matter, I'm talking about hot and dense matter. So I will tell you about what is hot and dense matter later. So currently I am focusing on the compact star properties, but in my PhD, I focused more on the in-medium properties of hadrons, like only the heavy ion sector, where I calculated the in-medium properties such as mass and decay width of hadrons, how it behaves in extreme matter.
I see. So we have prepared a questionnaire for you, so that you know to align with these subjects. So you are doing postdoctoral work in theoretical particle astrophysics. So theoretical particle astrophysics seems to intersect multiple fields, like it's intersecting, particle physics and also astrophysics. So how does your work integrate concepts from astrophysics and particle physics? And I can guess it also involves quantum mechanics. So can you explain us how your work, you know, integrates these concepts together?
Yeah, thank you for a very nice question. So when we talk about theoretical particle nuclear astrophysics, so we are saying about like four different fields, right?
We missed
But
that
in
part.
actuality, yeah, so in actuality, the thing is like the sciences cannot be categorized, physics cannot be categorized into like different section anymore. So it is not like 1900s, now it is 2000. So everything is mixed. So everything is interdisciplinary. So when I say I work in the field of nuclear astrophysics, I use some nuclear physics, I use some astrophysics, I use some particle physics. So if you ask me, when I was in PhD, I thought like I am doing theoretical particle physics, but later on I realized, okay, it's not theoretical particle physics, but it is a nuclear physics, more into nuclear physics. So, so what I use from particle physics, nuclear physics, or astrophysics, I would like to answer that. So when we talk about compact star, so when we talk about star, we think of a gravitational body, right? And the gravitational body, we think about a gravitational force with respect to it. But when we think more and we try to understand what is inside the star, like microscopic properties of star, then we think about particles. And then particles relate to nuclear physics or particle physics itself, right? So why we are more interested in nuclear physics, but because we are more interested into neutrons, not we are not interested in deep particle physics. Like we are not interested in like the decay width of heavy particles. So that's why we are more into nuclear physics. And since we are also studying the stars, that is astrophysics. So we are studying nuclear astrophysics, and since there are particle involved, so that's why it can be called nuclear astrophysics or nuclear particle astrophysics.
It seems it's a very interesting field. Sounds like a very interesting field. So since you told me that it's about studying the stars and the compact studying compact stars, then I can guess it's more about neutron stars and the other type, white dwarfs, right? So
Mhm.
these are the two main type of stars that you study.
Yeah, I mainly study neutron stars. My group also works on white dwarfs. I have not done that, but I mean, there is not much difference. The degrees of freedom in white dwarfs are different. Neutron stars are different. So I work on neutron stars. So neutron stars are mainly composition have a composition of neutrons. Um, and also what we do, we try to understand, we try to get the microscopic information from nuclear physics point of view. And from that microscopic information, we try to calculate the astrophysical properties of the star.
So generally, when I think of nuclear physics, I think of nuclear decay or nu two atomic nuclei or heavy nuclei colliding with each other, then fusing or breaking apart into many different nuclei. So how does that differ from the particular type of a nuclear physics that you study under this while studying the neutron star?
Yeah, that is very good question. So when we think about nuclear physics, we think about nuclear reaction, we think about nuclear fusion, fission. That is the basic idea of nuclear physics. We also learn about that vibrational mode, shell model, all that thing, but that are very basic. Right now, the research in nuclear physics are on the vibrational modes I have heard about, and some of the I have heard about the reaction itself. When you talk about the generation of a star, there is so much nuclear things going on. But in my case, I only use a part of it. So in a star, you know how a star is made. There is a life cycle of a star. So there is a nuclear fusion, sorry, which is the process which makes up the star, which gives the repulsive interaction to the star. And at some point of time, until the star develops this iron element, after that nuclear fissions come into picture. So these are few properties of nuclear physics which basically composite inside the star, and we are trying to understand the behavior of the star through the theoretical models.
Okay, so since you brought up the life cycle of stars, we know the very basics of it. Like first, a star is born, then it throughout its life cycle, it's fusing hydrogen atoms, and then uh, towards the end of its life cycle, like it runs out of its fuel and starts collapsing. And then while collapsing, it is for some a temporary period of time is again sustained by some electron degenerate pressure. Am I right? The electron degeneracy,
Yes,
the
in case
Pauli's
of
expression.
white.
Yeah, yeah. So
Yeah.
it is sustained for a temporary amount of time by that, and then if that too is insufficient to sustain that star, it again starts collapsing, and then it goes through another type of stabilization of some sort, like uh, this time neutron degeneracy, I think, right, sir?
Yeah, it depends upon the mass of interstellar dust, how big it is. So it can be categorized into two part. If the interstellar dust, the mass of the interstellar dust is like low mass, then through the life cycle of a star, and we get the electron degeneracy pressure, and the star we get after the collapse, after the nebula is formed, the core we call is a white dwarf. But on the other side, when we talk about heavy interstellar dust, when I say heavy, I'm not talking about like 500 kilograms. I'm talking about 10 to power 30 kilograms or more, even more, times 10 times more than that. So when we talk about high mass interstellar dust or nebula to start with, then the core we are generating is heavily strongly interacting. In that case, we don't have electronic degeneracy pressure, we have neutronic degeneracy pressure. It behaves like the same way. Neutrons are fermion and they repel each other because of the Pauli exclusion principle. That's why there is a Fermi degeneracy pressure there, which is playing with gravity. So basically two forces are playing with each other. Sometimes one wins, sometimes other wins. So there is a balance. Sorry, sometimes they are basically balancing each out. But when the one pressure wins, like let us say gravity wins, there is no more nuclear fuel inside the star which could resist the collapse, then the star collapse, and we call it core collapse. And then it goes to supernova, and if it is a very high star to start with, then it goes to black hole, otherwise it goes to neutron stars.
So first, a star can from a star after it runs out of its fuel, it can collapse into a white dwarf. Then, if it is still heavier than that, then it again collapses into a neutron star. And then, if that too doesn't sustain it, it either explodes or becomes a black hole. Am I summarizing it correctly?
The white dwarf doesn't go to neutron star directly. So white dwarf,
Okay.
if we have a white dwarf core, then it can start accumulating matter again from the surroundings. And if it is accumulating matter like in a huge amount, then it can start the life cycle again of a star, the whole life cycle of thousands of years. It can go to neutron star, or it can go to black hole, or it can go to white dwarf again. It depends upon how much mass it is starting with. So white dwarf doesn't directly go to a neutron star.
Okay, so the on the other day I was studying for this. I was preparing for this podcast, and I came across two limits. Like one is the Chandrasekhar limit, and the other one is the Tolman Oppenheimer Volkov limit. So these two are sort of limits that determine whether a star becomes a black hole or it becomes you know I, I genuinely don't know, but I know about these two limits. So can you please elaborate the difference between two limits?
Yeah, that's very good. So I would really like to talk about Chandrasekhar, sir. The Chandrasekhar limit restrict the white dwarf. Like it tells us like 1.4 solar mass, a white dwarf can maximum hold 1.4 solar mass. It cannot hold beyond 1.4 solar mass. If the star holds beyond 1.4 solar mass, then it goes into black hole. So this is first thing. And about TOV limit, so first of all, Tolman, Oppenheimer, and Volkov equation. I would like to talk about this equation because this is very, very important and beautiful piece of work by these three scientists, which basically connects the microscopic properties of a star, such as pressure, energy, density, to the macroscopic observable of a star, like mass and radius. So you can think like if we are on Earth, obviously, and we want to predict what is the mass that particular star is holding, or what it is composed of. So that is what we can do right away by using some equation or plotting. And the Tolman Oppenheimer Volkov doesn't give, if I'm right, doesn't give a particular number to it. So it is roughly like 2 to 3 solar mass. So if so initially we believe that beyond 2 solar mass there could be a black hole, but right now, due to experiments like NICER and LIGO, so we are having results like which a fast rotating star can also have 2.5 solar mass. But when we talk about 3 solar mass, we are more into black hole, like it could be a black hole, but not a neutron star. So this is a very vague line in between these two categories when we talk about neutron stars and black hole.
I see. So the Chandrasekhar limit was obviously derived by Sir Subramaniam Chandrasekhar. I believe he had a very good handwriting. I was just looking through his work, and I came across a picture of him, uh, explaining a certain concept on a whiteboard, on a blackboard. Whiteboards were not there during his time, and I noticed that he kind of had a very pretty handwriting, and just we are going out of topic. And the next thing is that the Tolman Oppenheimer Volkov limit, we only remember Robert Oppenheimer when it comes to the atom bomb. But yeah,
Mhm.
a lot of us don't know that he was also into the theoretical astrophysics and solving these equations, Einstein's general relativity, with his students. And he came up with this beautiful, not him, his team came up with these equations.
Yes,
So
yeah.
so the next question I would like to ask you is that what inspired you to focus on this particular area of research?
To answer this, I would like to start with the quote. A teacher's true legacy is not the lesson they teach, but the curiosity they inspire. So it was my teacher who lit the flame of curiosity in me and guiding me towards this research path. So when I was in my bachelor's, so I was doing physics like a normal guy. I have no such special interest in any particular field. But then there a teacher comes. I will say his name, Dr. Rajiv Kumar Parashar from my bachelor's college, and I got a huge inspiration from him. The way he thinks, the way he teach about the physics idea in a very simple manner, and I got curiosity in physics. Then I got a second teacher who inspired me a lot in my life, who was Dr. Sandeep Sahajpal, Professor Sandeep Sahajpal from Punjab University, Chandigarh. He taught us astrophysics. So when he taught astrophysics, he started from Big Bang theory to the date. He discussed everything about the universe, like from starting to the current state, discussing about evolution of the universe, about quark gluon plasma, about hadronization, about how the stars are made. So it gives me a clear understanding of how I would not say clear. It gives me give me a good understanding of how universe is working, and what is the idea. What is the I also relate it to my life as well. So this was the point where I got interested in astrophysics. So I was more interested into astrophysics in the beginning, but later on I also developed an interest into particle physics, because I wanted to know how universe was started. Like what about the Big Bang theory? What about the class quark gluon plasma? What about the hadronization? And this led me to deep dig inside these categories such as particle physics, hadronic physics, and then I started exploring opportunities, like PhD opportunities in these areas, and eventually I landed in NIT Jalandhar, which is where I mainly studied the research of in the area of hadron physics, which is a subcategory of a particle physics.
Okay, so you also studied the uh, behavior of hadrons, like in extreme conditions, right? So you have earned your PhD from Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, focusing on properties of hadrons under extreme conditions. So if I'm not wrong, hadrons are particles made of quarks that are held together by the strong nuclear force. And there are two other categories called leptons and gauge bosons. So can you shed some light on these classification? Like we are talking about hadrons, we're talking about fermions or leptons. So can you just enlighten our audience about how we classify the particles like this?
Yeah, sure. So when we talk about hadrons, like we don't have to get inferior about the names. Names are just the names. So hadrons are basically a classification of baryons and mesons. So baryons are fermions and mesons are bosons. And then we have as other category leptons, and then we have gauge bosons, which are mediators between the forces. So we are interested in strong interaction physics. So in the strong interaction physics, the particle that interact, that play with each other, is baryons as well as mesons. So in context of my research, you wanted to ask, or what?
So it would be better if the audience knows about the classification before we talk about these things in detail.
Okay, then I can say, so when we talk about elementary particles, so elementary particles are the particle that are indivisible, that cannot be further broken into. And the elementary particles can be divided into two categories. One is leptons, and second one is the quarks. So leptons and quarks. Lepton participate, they have charge, and they participate in electromagnetic as well as weak force. And when we talk about quarks, quark mainly participate in strong force. Because of their strong nature, they have a color charge. They also have like electric charge, but in comparison to strong force, they don't feel much electromagnetic force. And from these quarks, if we have three quarks, we can do permutation and combination, and we can create as many hadrons out of it. And if we join three quarks, then we get baryons. And if we join one quark and one antiquark, we get mesons. So why to join only three quark? Why to join one antiquark and one quark? Because of the color neutral nature. So only three quarks in baryonic form, in fermionic form, can give us a color neutral particle. And similarly, a quark and antiquark pair can give us a color neutral particle, which is a boson, which is a meson. And these baryons can be further divided into like nucleons and hyperons. We know about nucleons like proton and neutron, but hyperons we don't know. Only the master in physics people would know, or BSc as well. So in that case, a nucleon with a strange particle in it, with a strange quark in it, is called hyperons. And on the other side, mesons, when we talk about mesons, we have like plenty of them. So we have a quark antiquark combination, and if we are only restricted to SU3, when I say SU3, I'm talking about only three quarks, up, down, and strange. I'm not considering SU6 because the next three quarks are heavy, so they don't exist in nature like in the normal condition. Therefore, I'm talking about SU3. From SU3, we can create as many as mesons from the permutation and combination. This is not a simple permutation and combination. There is a much underlying physical and mathematical perplexity into it, but just in a naive way, I'm saying that. So that can be divided into like pseudoscalar mesons, scalar mesons, axial vector mesons, and vector mesons. It are divided with respect to their spins. So from these, all these things, we have a recipe, and we collectively we call it as a particle zoo because we have plenty of them, and we are really proud of our scientists or experimentalists who can really predict that this that the pion is different from kaon and electron is different from proton. So these are very challenging concept.
So in case the term color charge came up, so in case the audience is wondering, color is has nothing to do with the regular color we observe in nature. It's just a convention, a name that we gave, right? Like it's one more property, like the positivity, negativity of charges. So there was one more property, and we named it color to add to the confusion, as if this
Yeah, yeah.
thing was not confusing enough. So.
We talk also when we talk about electrons, for example, there is a spin. So in reality, we don't know whether it is really spinning or not. And electron doesn't follow a discrete path. It has a orbital, so it has a probabilistic nature. So when we talk about quantum mechanics, we talk about more abstract idea, more mathematical idea. When I teach my student, like if you want to learn quantum mechanics, then leave your classical cap outside the room. So you cannot think quantum mechanics while wearing your classical hat. You cannot think it as a ball. You have to try to understand it more in a more abstract manner. And similarly, when we talk about quantum field theory, like this is the concept we are talking about, color charge is a more into quantum chromodynamics. The color is a mathematical abstract idea which differentiates one quark with other quark. It has nothing to do with the color, but it is a very good analogy because red, green, blue makes it a color neutral because it is a white.
So it stems from the idea that uh, you know, in digital technologies, we use red, green, and blue to produce different types of colors in on screens and all that. So the idea stems from that. Uh, so